Hello everyone, welcome to this lecture of two-phase flow. My name is Mingchang Li. I'm currently a faculty at the Department of Power Mechanical Engineering in National Tsinghua University. Per the request from the university, I'm recording and sharing this series of lecturing for NTHU OpenCourseWare. The topic of this lecture is about liquid-vapor interfacial instabilities. The content of this lecture material is based on the book Liquid Vapor Phase Change Phenomena, authored by Professor Carey. Instabilities of the interfaces between liquid and vapor have a strong impact on the heat and mass transfer at the interface during phase change processes. The morphology of the interface is affected by the stability of the interface. From the previous lecture, we have also seen that the transport across the interfacial region is greatly affected by the surface of the interface. From these four figures on the right, it can also be seen that the characteristics of the flow patterns in two phases are highly dependent on the interfacial surfaces between vapor and liquid. The flow pattern is also critically important to the heat and mass transfer associated with two-phase flow. Therefore, in this lecture, we will discuss about some basic concepts of interfacial stabilities between two fluids. Considering the case shown in Figure 4, a vapor or gas phase flows on top of a liquid. The direction of gravity is pointing downwards in the negative z direction on this figure. Initially, the interface between the two phases is assumed to be a flat horizontal plane. uv is the free stream velocity of the vapor phase, and ul is the liquid velocity correspondingly in the horizontal direction. The goal here is to determine the range of conditions for which the interface is stable with respect to an arbitrary perturbation of the interface. Consider the viscous effect is negligible and assume the fluid is incompressible Newtonian fluid. This set of standard continuity and momentum equations on the x and z directions can be obtained as shown in the upper portion on this slide. Then, the velocities u and w, as well as pressure P, are decomposed into two parts, corresponding to the base flow and the perturbation, respectively. For simplicity, here we also assume that the disturbances to the interface is only dependent on x and t. The problem is then subjected to a standard linear theory analysis. Without going into much detail, which could be found in the textbook, the final result for the dispersion relation is shown here. From equation 43, beta has an imaginary part if the base flow velocity for the liquid or vapor is non-zero. This implies that any horizontal velocity component in either fluid will produce waves at the interface. If beta has a positive real part, the amplitude of the perturbation will grow with time. This will happen if the value of the first braces is positive. To investigate the condition that beta becomes a positive value, the terms in the braces is rearranged to equation 44. It can be seen that the right side of it has a minimum value at a critical wave number alpha c, shown by equation 45. A critical velocity corresponding to this critical wave number can be obtained as shown by equation 47. If disturbances of all wavelengths are present in the system, The interface will be unstable if the absolute value of the velocity difference between the liquid and the vapor above it is greater than the critical velocity. This type of interface instability is called as Kelvin-Helmholtz instability. With a specified disturbance wavelength or wave number, equation 44 can be used to estimate the required velocity difference that leads to an unstable interface. If the gravity is set to 0 in the previous derivation, the dispersion relation of beta for a vertical interface or at 0 gravity can be obtained. The criterion for the interface to become unstable is shown by equation 50. Since there is no minimum value for the term on the right, if disturbances of all wavelengths are present, there will always be some disturbances, particularly those with long wavelengths, be amplified. By changing the sign of the gravity in the previous derivation, the dispersion relation for waves on an interface for vapor under liquid can be obtained. In this case, the fluid with higher density is above a fluid with lower density. The gravity tends to make the interface more unstable, where surface tension tends to stabilize the interface. Note that the right side of equation 49 also does not have a minimum value. This means that if disturbances of all wavelengths are present, some of them will amplify. If the velocities in the liquid and vapor phases are both 0, interfacial stability relations for a motionless liquid sits on the top of a motionless vapor can be obtained. This condition is called as Rayleigh-Taylor instability. The critical wavelength, lambda c, that corresponds to the critical wave number is shown by equation 52. The maximum value of beta from the dispersion relation is obtained by taking differential of beta with respect to the wave number alpha. This disturbance wavelength corresponds to alpha max is called the most dangerous wavelength, lambda d, because it leads to the maximum possible real number value of beta. Disturbances with wavelengths near lambda d are expected to dominate the early stages of the instability of interfaces. One example in the daily life is that if a jar contains liquid is put upside down with the mouth open, the interface of the liquid to vapor at the opening gets more easily unstable with a bigger mouth. In later lectures, the concept of Taylor instability will be used for analyzing the stabilities of the liquid to vapor interfaces and the associated heat and mass transfer in boiling processes. Here let's watch some videos that we have also seen previously in Lecture 1 about interfacial instabilities. Analysis for the interfacial instabilities for a liquid jet can be conducted by a similar procedure. The flow of a liquid jet from a nozzle tends to break into small droplets after traveling some distance in air. This phenomenon is important to many engineering applications, including fuel jets in combustion engine, spray cooling, sprinkler, and the breakdown of liquid columns or films into dispersed flow in convective film boiling in tubes. Here we show some important results. Detailed derivations to these results are available in the textbook. The liquid jet becomes unstable for axisymmetric perturbations with wavelength greater than the circumferences of the jet. Also, the wave number and the wavelength correspond to the fastest growing of disturbances are shown by equation 88. The time required for the disturbance to grow from its original value, delta 0, to R0 is given by equation 91. With this information and the velocity of the liquid jet, the distance downstream of the nozzle for the jet to break up, ZB, can be estimated. Example 4.3 from the textbook is shown here for illustration of how to use those results. For a water jet with a diameter of 0.5 mm and a velocity at 3 meters per second, the breakdown distance is approximately 9 centimeters. In this lecture, the concept and a linear theory approach for analyzing the interfacial stabilities on the liquid-to-vapor interfaces are introduced. There are two types of interfacial instabilities. The Kelvin-Helmholtz instability happens when there is a velocity difference between the liquid and the vapor above it flow in parallel. The Rayleigh-Taylor instability happens when the liquid sits on top of vapor. Critical values on the wave number and the wavelength correspond to the determination of interfacial stabilities are presented. These results and the relations of the interface stabilities will be used in later lectures for analyzing heat transfer characteristics with phase change.